and you've learned a few different reagents which can be used, and you can actually prepare amines. Reductive amination is a very convenient way to convert that group, the carbonyl group, into the, in this case, fully saturated, again sp3, because we added this hydrogen, and then obviously there is another one implicitly present here as well. We added a molecule of dihydrogen across. You can do it by hydrogenation, you can do it by hydride transfer reagents. All of that starts with the H- attack, still nucleophilic attack, at this modified carbonyl carbon. So for you, pattern recognition is that this is nothing more than a carbonyl, masked carbonyl. And if we get to this masked carbonyl, having more than one may lead to formation of interesting heterocycles. So dicarbonyls, 1,2, 1,3 dicarbonyls, and dinitrogen compounds, sulfur, nitrogen, and so forth, are your very easy entry into the world of the heterocycles. Unless there is a very explicit, just like it was on the not multiple choice, the predictive product questions on the last exam, very explicit leading group which is going to take off, you are expected only to know generalized structure of the heterocycle that you are formed, keeping in mind that what drives formation of the cycles is stability of the 6 and 5 membered rings, and after that, aromatization. So most of the heterocycles, you will never be asked to form a heterocycle which is not aromatic. How it happens is, don't worry about it. You don't need to know every single method. If you know them, it's oxidation. Obviously, you need to remove some hydrogens from it, so it would be some kind of oxidation. But I didn't teach you that. I only taught you the main disconnects where you need to know how to assemble those heterocycles, mostly from dicarbonyl compounds, which are 1, 2, in some cases 1, 3. And then we bring rings by substituting these oxygens with nitrogens and putting a clip of 1 or 2 carbons or however many you would like to have in that ring. Nitrogen, oxygen, and sulfur are the only heteroatoms we are going to use in heterocycles, and we never use any other ones anyway, so you don't need to learn anything new on that. And oxygen and sulfur are close friends. They behave exactly in the same way, except sulfur is a little bigger, it's a little softer, but as far as you are concerned, whether it's thiazole, oxazole, or a heterocycle whose name you don't know and remember, you don't need to, because we will synthesize it based on these simple transformations. If we are looking at the carbonyl group from slightly different perspective, we learned that we can actually make carbon-carbon bonds very nicely and conveniently if we have phosphorus ylides. We looked at the 2 different types. We have plus minus phosphorus ylides, which are prepared most of the time from alkyl halides plus triphenylphosphine. There was a little modification which we called Woodward-Emmons modification of the therapeutic reaction, so Horner-Emmons rather. Sorry, it's which is not that big of a deal. You are looking only at the phosphonates. As a potential side chain, the reactivity is exactly the same. Butyprotonate, usually sodium hydride, butyl lithium, sometimes sodium carbonate would suffice in particularly acidic cases. And what happens here, you will actually replace your whole oxygen with the carbon which came from this Wittig reagent, which originally was in the halide. Those we've done with you quite a bit, so Wittig inevitably makes it actually physically on this exam. I know the question where it shows up. So be familiar with the basic Wittig and minor distinction if you need to know between Horner-Emmons and the traditional triphenylphosphine-based Wittig. What are they not compatible with? What are the reagents which are required in both cases to get this negative charge? Usually strong bases. So protic solvents are no-go, acids are no-go, by the same token. So they're going to be done in THF and benzene and any other solvent which is not protic. The only reaction pretty much of the aldehydes and ketones which has to be done anhydrously well, in addition to obviously our Grignards and any other nucleophilic additions which are happening through the organometallic chemistry. The only organometallics, are Grignards and lithiums. Since I'm bringing up lithiums, the logical point now to make any nucleophilic reagent which you just started to cover in the beginning of your organic chemistry adventure with Travis and then continued with me, we were looking at bases and nucleophiles basically being part of the same family. They are nucleophilic, and therefore they are basic, and therefore they are nucleophilic. That's no longer true, right? So we have both options now. We've learned that ways to use different types of bases, either to add as a nucleophile to this carbonyl center, or act as a base, and now we are making differentiation between our nu and UMB, purely acting as a proton removing reagent, because the outcomes are going to be totally different. So if we have our tetrahedral intermediate formation, in this case without deprotonation, versus formation of the enolate, which is nucleophilic at this carbon. And that's where we came with all of our N and P sites and learned that we can use a very strong base, for example, lithium amide, which would be hindered and won't add at all to the carbonyl. Or if you use Grignard, if you use amine, they're obviously going to be adding to the carbonyl group itself. That table at the end of chapter 17, I believe, 5 slides on the acids, bases, what adds as a nucleophile, what removes the proton instead. What's the difference between lithium reagents as opposed to the Grignards, which always add to the carbonyl, and lithiums give you a mixture, and then you learn a little bit about the cuprase as well. Those 5 slides are your friends. They're useful both from the enolate chemistry viewpoint and thinking about what kind of derivatives you can get out of aldehydes and ketones under very mild conditions, to the more aggressive ones when we started assembling and lithiating under kinetic or thermodynamic conditions the specific CH bond. But this is our first foray into the carbon-carbon bond-making reactions which don't involve aggressive Grignards. And the beauty of this chemistry was, of course, that a molecule of an aldehyde and ketone in principle possesses 2 reactive centers. We can look at it as the electrophilic species if we are adding directly to the carbonyl, or in the presence of hydroxide, for example, we said that dilute sodium hydroxide is strong enough to pull away this hydrogen, and that with the enolate under very, very mild conditions, and that enolate can now add to another carbonyl, whether it's coming from the same molecule or another one, making our first carbon-carbon bond under pretty mild conditions. I did it on purpose in the vertical way so you can feel how electrons are literally falling down from the higher energy state all the way from oxygen, following down to this one. You preserve your negative charge, right? So O minus here, which has converted it into, if this is R prime, going to be R prime molecule still with a negative charge on it. And then we can capture it and then we can eliminate. And some of the most beautiful compounds we've learned to make were our alpha-beta unsaturated compounds, where we started to learn a lot of interesting and important reactivity, which was vinylogous, and vinylogous reactivity, you know how much I love, so it will come to on the exam. When we can conjugate a double bond and use it effectively as a conduit of electron density from the carbonyl all the way to the R's, which are connected on the side, and we can have more than one double bond, we can have all the way electrophilic, nucleophilic sites migrating, but now we have 2 electrophilic sites. Nucleophiles can add in a direct fashion and in the 1,4, or we called it Michael addition fashion. Therefore, the molecule with a double bond in the carbonyl becomes a Michael acceptor. It accepts nucleophile in the 1,4 or conjugate addition fashion. And your favorite one out of them all, go-to, is a cuprate. Simple, unambiguous. Your favorite one to add to the carbonyl is Grignard. Again, simple, unambiguous, relatively aggressive. Everything else has a gradation of a little bit of here and there, and we decided that, or we agreed that softer, not as charged, relatively big diffuse nucleophiles will usually, which are big bases, usually add in the Michael addition fashion, as opposed to small, strong, pointed bases will always add in the carbonyl, to the carbonyl. This is the part where I think that question maybe not directly involved in it. Well, it will show up if you decide to go that pathway on one of the synthesis on the exam. When we are talking, we spoke about it before, let's quickly draw parallels and differences between our lithium and our MgX compound Grignards. Lithium is tiny, small formally. And this is, I think, where a little bit of a disconnect came for some of you, that if this is small, therefore it's going to be hard, therefore it's going to be more nucleophilic, when in reality, the covalent character between lithium and R is much, much higher than between R and magnesium. First period, tiny, small, perfectly happy to engage in true covalent interaction, even though polarized, it's still more basic. It's not ionic bond by any means. Grignard is almost ionic. Grignard is almost R minus MgX plus without any deltas on it. Effectively, if you are able, Grignards in very exotic cases can be isolated as compounds without a solvent, but if you were able to isolate it, it would be a solid salt. It would behave as a salt. Lithiums can be distilled. Metal lithium is a liquid. It behaves as a liquid, as a strong base. You can metal lithium, butyl lithium, many of them are actually non-crystalline compounds attesting to how non-polarized this bond is. So just remember and keep in mind, base primarily nucleophile. Lithium as a nucleophile almost never used. You will never see lithium nucleophiles. And if you need to nucleophilically add something, maybe it's cuprate, if you need in 1,4 fashion, maybe it's Grignard, but never a lithium compound itself. So let's make that distinction clear, because you will have that choice, I think, on one of the questions. So that's as far as our additions go. Obviously, we didn't stop because here at the aldehydes and ketones condensing with each other to get alpha beta unsaturated compounds. We started crossing them with esters. And that's for a Claisen reaction. That's the only one, by the way. Amides don't work. Acyl halides can be maybe on a good day engaged with some coercion, but in reality it doesn't happen. So we only literally have aldehydes, ketones, and esters as far as enolates are concerned. The difficult part with these ones, that the reaction is ending up being actually thermodynamically unfavorable. It wants to go back much more than to go forward as you are forming acetoacetic ester out of ethyl acetate. The reason is that delta H is about plus 13 kcal per mole. So it's thermodynamically not favorable, and you need to have a full equivalent of base in order to get to the stabilized anion structure as a product, and then you quench it. Big difference between all of the aldol chemistries, which we've done with the enolates, aldehydes, ketones alike, and Claisen, that you don't have a choice but to use a full equivalent, and that's a big difference. If we had dicarbonyls which didn't have a choice, and these hydrogens were substituted by Rs, and they didn't have a choice of being deprotonated, whatever this is, so even if they can be deprotonated on this side there, OH attacking any of the more reactive carbonyls, and now you have a choice obviously between potentially aldehyde and ketone, or maybe ester and ketone. Since this poor thing doesn't have any way to release its negative charge, it actually fragments and does retroclysine. Retroclysine or retro-type block dicarbonyl reactions are most common when you need to reduce the chain size of the molecule. When you see two carbonyls in 1,3 orientation and you have full substitution between them, that molecule most likely is going to be used for fragmenting. You would like to fragment it under basic or acidic conditions just as well. But block dicarbonyls are critically important for both pre-assembling and then destroying the chains or eliminating some of the functional groups for decomposing carbon-carbon frameworks, which we don't do all that often, even with aldehydes, ketones, with retro-aldols, mostly aldol, retro-aldol chemistry we employ, but not a whole lot. We did a question on that in the third exam. The one with the cyclic acetyl-ketal, I recommend you revisit it, have a look at it. It's useful to remember as well for the exam, make a note of that. The question on the last exam, I think last exam, not last exam, previous exam with the different ring sizes, aldehydes, ketones with the acetal protecting group, the basic conditions versus acidic conditions and so forth. That's as far, again, what you need to remember from this are 5 slides at the end of chapter 17, which I called carbonyl review for you. They are all in color. You will be using Michael, you will be using aldol one way or another, you will be using some type of lysine potential reaction. And what we learned about it, if we'd like to have a very good control of those reactions, we need to eliminate amphiphilic character, the dual nature of one of the carbonyl components. We want to make it only an electrophile. Usually that means non-enolizable. We introduced, for example, benzaldehyde as a non-enolizable aldehyde. We introduced formaldehyde as a non-enolizable. These are purely E components. They cannot do any nucleophilic chemistry. They only act as electrophiles. So therefore, you're in your control. You're able to reassemble molecules, or assemble molecules with absolute selectivity if you are using whatever nucleophilic component you are getting from another carbonyl to them. No worrying about cross-contamination or any kind of cross-reactivity. And on top of that, they are particularly reactive because this one doesn't have any R's, and this one has an aromatic group if you open it up, which stabilizes the carbonyl by delocalization, or your favorite resonance theory, which I haven't heard it for the last month almost at all. So I trained you well. I weaned you out of that baby bottle of resonance being the universal answer to all your problems. Okay? Carbonyl chemistry in a nutshell. So it's, I know it's 45 minutes and we only did carbonyls. I'll be relatively fast, don't worry, we'll finish the rest. The rest was, let's skip that CO2 slide, it's way too important.
Carbonyls is like the major, the entire course basically.
The rest, and conceptually, don't try to divide this into 2 separate chapters. Now look at it in a one wholesome way, because these reactions be covered in heterocycles and aromaticity, and then you started covering aromaticity, to be honest, in the very beginning when we did the Salter 6-pi transition states and the stabilization of the pericyclic reactions. Let's just put a very important one common denominator for all of them, because on the exam, again, I'm not going to be able to split it. I didn't split it into the sub-chapters. You'll be looking in a very wholesome way at both aromatic compounds, which are carbon-based, and heterocycles all together, even though we don't do well on the one of the exams we did will solve a little bit of the on the benzene, but that's so easy to recognize that it's not even worth reviewing it. I don't think I honestly have it in solver. Fine. But you look, what you would like it. It's I can always incorporate some. It's not difficult, but I don't think it's necessary. Plus it's a relatively straightforward, easy reaction for you guys, so you know it so well. So the important part about the aromatic rings, when we got to the, and I'll do it right away side by side. And I'll do this one, I guess I should do it right away in the -4. 5 and 6 membered rings are the only aromatic structures we cared about. I'm not going to go to condensed structures with naphthalenes, with the 6,6 or potentially 6,5, except for the indole because it's part which we covered, so you know roughly what to expect there. But benzenes and 5-membered aromatic rings and heterocycles are by definition nucleophiles. The electron-rich structures, how rich now? We're obviously going into the gradient and gradation, which is pretty broadly distributed all the way from extremely electron-rich or Rs, or I'm doing it on the same molecule, it doesn't mean it's part of the same molecule, or NHR, which are dumping electron density despite being electron withdrawing, electronegative elements into the aromatic ring through lone pairs. First, most important lesson we learned in chemistry of aromatic compounds, lone pairs are cheap. Pulling electrons through sigma bonds is expensive. It's much easier to donate than to pull away, even if it is an electron withdrawing oxygen, because moving electrons through a sigma bond costs you actual kilocalories. Dumping free lone pair is almost free. We call it mesomeric effect, and you draw different resonances, true resonances in this case, by activating and deactivating these rings. We learned that any group which is activating or donating will always allow substitutions to happen in the ortho and para positions. We don't have a control over ratios usually. Most of the time we get ortho and para mixtures. There is one trick. You obviously have very large electron donating group or very large activator. Will probably not allow you to introduce any ortho substituents. And if you want to block the para position, you sulfonylate it, because the sulfonylated one, sulfonic acid, only goes in the para position simply because its huge is big and can be removed reversibly under acidic conditions in water. So you have a protecting group again for actual CH bond in an aromatic ring. Very unusual protecting group. It's a placeholder effectively, it just holds the place. Does change reactivity of the ring a little bit, it's electron withdrawing and so forth. If we get to the electron withdrawing groups, these rings are inherently more stable. They are less reactive altogether, and they don't want to undergo substitution, but if they do, very slowly, electrophiles are going to, I shouldn't be drawing it in this way, but it's attacked by these two carbons. And again, you can draw the resonances and explain where the positive charge ends up, why it's particularly beneficial when we put a substituent in the meta position, because it never gets next, positive charge never gets next to the electron withdrawing group, which would be destabilizing type interaction. Here, exactly the opposite way. We get positive charge next to electron donating group and stabilize that intermediate. Everything about intermediate stabilization, about reactivity of the aromatic rings is dictated almost exclusively by mesomeric effects. And then when we graduated to the 5-membered rings, we started looking, for example, at pyrrole. We started looking at the key ones, imidazole, for example, and they became very important. Pyrrole maybe not as much, but when we get an aromatic ring on the side, we learned that this compound is called indole, also a side chain of an important amino acid. But they're, in general, always less reactive. In general, you will be even less reactive when you get to the 6-membered ring. For example, you have single nitrogen, 2 nitrogens, pyridine, pyrimidines, pyridazines, and so forth. All of those molecules, in principle, can be assembled through the carbonyls, and we've learned roughly how to do that, even if we didn't go through every single detail. But we learned that the 6-membered rings containing heteroatoms are much lower in reactivity toward electrophilic aromatic substitution than your 6-membered rings, which are carbon-based. 5-membered rings depends on the substitution, can be stronger, can be more reactive, less reactive, but the more heteroatoms you get in them, in general, less reactive they become. But they still can be nitrated, brominated, whatever we choose to do to them, and alkylated. So you can get all kinds of different types of imidazoles, and many of them are found again in amino acid derivatives and some of the drugs and some of the compounds which are critically important because you can modulate acidity of this NH based on what kind of substituents you have in the molecule. Practice very quickly your resonances for 5 versus 6 membered rings and different substitution types. Where would be brominate, where would be chlorinate or alkylate these molecules, because it's not like 6 membered rings. Here you're going to be jumping in alternating circles because of the odd number of atoms in the Sketrel cycle. So stabilization is not very, very trivial. You'll have to draw your intermediates out and to appreciate where, for example, bromine goes when we are brominating, or nitrogen, or anything else that we are doing, right? Substitutions, electrophilic aromatic substitutions, there won't be a question on the, describe the mechanism of electrophilic aromatic substitution or nucleophilic, for that matter, substitution on benzene. Boring, uninteresting, doesn't really matter. But you do need to remember, and it would help you probably knowing what kind of substituent effects are present in the molecule if we need to include it in synthesis. I covered that in the synthesis rather than predict product questions or do any 1, 2, 3 steps. It's going to be your steps. You choose how to assemble. And again, to reiterate, as a footnote, strategy is always worth more. Strategy is usually 66%, execution is 33%. If you know the strategy, you are in a much better situation. So do the synthesis, and even all of the synthetic sequences only disconnected properly without any reagents will always earn you more credit than all of the synthesis completed semi-properly with the correct reagents, but not accurately leading to the desired molecule. So think about broader strokes rather than the finer details. My goal is not to test you on the tiny little details which you in principle can look up. If you say a non-nucleophilic base and you forgot that it's an LDA or a triethylamine, fine, so be it. You'll look it up. But if you don't know that you need to use a base to deprotonate, that's going to be an issue. So that's not going to be salvageable, obviously. So be careful, and if you forgot something, please don't panic. Just show that if you need a base, okay, it's a B, not a nucleophile, not an NU. And that's all you need to show to get the majority of the credit already for a particular transformation, for a particular synthesis. Again, no specific, no exotic reagents, nothing like that. One important reaction which we covered with you for aromatic compounds was the formation of diazoniums. And Shiori did a few, I don't know if many of you, all of you, or maybe some of you at least looked at it at the review sheet. It's pretty comprehensive based on a lot of the reactions which we did in class, and then some synthesis. I think are important for you to look at like sulfonamide synthesis. We did another drug, right? Remember sulfadiazine was also based on the sulfur substitution, diazonium chemistry. And diazonium chemistry may be useful to you. It's up to you whether you want to use it or not, but be at least familiar with the fact that you can get, and draw it, please draw it, because I won't know if you just say diazonium again. I'm dyslexic as far as words are concerned. It's, so you gotta use, give or take, right reagents at least. KNO2HCl, and then it's going to be ECl minus. And here you have a multitude of different things which you can introduce. Do not look at this reaction. I know you kind of tend to look at this reaction as a nucleophile coming in and kicking out a molecule of dinitrogen, substituting it in your mind may be convenient, but whether it's I minus, whether it's OH minus, whether it's water itself to make phenols, to make cyanides, to make anything you want in here. Usually, just for your information, copper mediated is always easier than without copper, but even if you know methods without copper, that's perfectly fine. But these are the only ways how you can easily synthesize phenols. Please do not, and I know we corrected it all, it did appear in one of the SI sheets, but you can, under some magical conditions, convert chlorobenzene into phenol. You won't. Even if you do it in the 300 atmospheres and you do it in the molten sodium hydroxide, it's a very slow process, lousy, not good. You are not going to be able to do it in the lab. So the fact that it's in principle possible doesn't make it a creditable offense on the exam. So don't do it. It doesn't work. It doesn't look right. And even though I know some of you attempted to do it on the previous exam, so I taught you now that it shouldn't be executed in this way. But there are plenty of ways to stitch together molecules, whatever nucleophiles you are using here, in the presence of copper, to get many types of derivatives of the aromatic compounds. The only thing that I left out are the amines themselves, which we covered sort of tangentially, and one of the methods which you should be very familiar with is your Gabriel synthesis, in addition to reductive aminations, which you did with the carbonyls. Because when we get to succinimide type derivatives, you can deprotonate them and make them into a decent nucleophile, which can go after usually primary halides. And this is a very clean way to make a carbon-nitrogen bond way cleaner than you would do with reductive amination, for example, or in some cases just straightforward substitutions. And then hydrolysis, which is usually accomplished with hydrazine, but if you forgot, you can do it with KOH, and you can do it with other basic conditions. You can release your amine. Limitation is primary amines. The advantage, primary amines are some of the most useful ones most of the time. They can be, if you need to reductively aminate, that aldehydes be used for reductive aminations pretty efficiently. And there is a plethora of all kinds of different halides which you know how to make out of alcohols, which you can do by bromination of the side chains of aromatic compounds, which you can really, then you've learned many different ways to convert everything from hydrocarbons to alcohols to even carboxylic acid derivatives and so forth into them. Then you can do all of the chemistry of the amines from here, including heterocyclic chemistry. So if you are asked to prepare a heterocycle and you need to make an amine, if it's not given to you, you have a way of making it usually through, since you need to have primary, like I said anyway, you have a way to do it through Gabriel. No other method would allow you to do it as cleanly. You can do reductions, you can do all kinds of other manipulations that you learn, but I think this is, in general, your go-to method and the easiest one. So I tried to fit, I'm not going to do carbohydrates again, you remember them pretty well, so we did amino acids and peptides just now, so there is no sense doing that. Review of that. I did want to fit it in an hour, but we have as much time as you want me to go over anything that you'd like me to explain, re-explain, emphasize, anything that bothers you from your notes or from the SI review or from any other from the previous exams. Please feel free to ask. Everybody will benefit from it, I think.
Is there going to be rank the following questions?
Yeah, probably. On the first page, I still included a little bit of the acid bases and electrophiles, nucleophiles. Yeah,
Okay.
I did. Yes, the rank. The first page is probably multiple. Well, I guess it's multiple choice, effectively, right? Or circle the right answers type questions. Yes, and those are both in terms of acid base. I had to mix it all together. The acid base, the electrophilic reactivity, nucleophilic reactivity, and the aromatic electrophilic substitution. What will participate better in those particular transformations? There are a couple of
Questions about the overall energy reaction.
Yes. Choose the right structures,
Yeah.
maybe for carbohydrates as well. I know it seems like a lot of material, but in general, your thoughts are, I'm sure, pretty well organized. When is the first exam? Wednesday was chemistry your first exam. Chemistry is your first exam. Well, I mean, you have other ones, I know you need to prepare, but my recommendation, if you could, and it works usually very well, Tuesday night is the last day you study for chemistry. Leave Wednesday alone. Study for something else. You'll be much better off because it will settle in your head better than doing it the night before. And please sleep the last night. So it's don't study for it because
Isn't this-
well, the less you sleep, it does correlate for most of the people, and I'm used to doing a lot of writing and a lot of work at night, but next morning still something to catch up with. You need your clear head and you need to be on your best performance in terms of being rested, calm, and go through the questions one by one and in a very, very cold-blooded surgical manner. Anything else? Anything that? Yes.